Does advanced accelerated applications also include anything?
It did. Accelerator production of tritium until this year when Congress specifically zeroed it out. What are two places in the budget authorization? They said there is no money in two different places in law. They wrote the same shit.
Okay. Let's begin. Let me have your attention. Let's begin. It's my privilege to welcome you to the University of Tennessee Nuclear Engineering Department Seminar Program. Today's speaker is Dr. Denis, who is a staff member of the Los Alamos National Laboratory. Denis received his PhD in nuclear engineering from Purdue University in 1986, a master's from the Air Force Institute of Technology in 1981, and his BS from the University of Colorado in 1976. Although he's a staff member of Los Alamos right now, he's currently on sabbatical at the Harry Reid Center for Environmental Studies at the University of Nevada at Las Vegas. He's a longtime friend, very active in the American Nuclear Society. He's a very strong advocate for nuclear technology, particularly nuclear power, which is what we heard last night in his presentation to our local ANS student section. Today's presentation is entitled Advanced Accelerator Applications and Transmutation of Nuclear Waste. So it's indeed a privilege for me to present to you Dr. Bellow.
Thank you, Lee. Thanks for inviting me here to give this presentation. Guess I better grab this little funny mouse thing. The Advanced Accelerator Applications Project is a fairly new project of the Department of Energy's Office of Nuclear Engineering, Energy Science and Technology. It started out as the Accelerator Transmutation of Waste project at Los Alamos National Laboratory about 10 years ago, and has evolved into this much larger Advanced Accelerator Applications project. The initial research was done as part of a laboratory-directed research and development program at Los Alamos, so it was funded out of Los Alamos's discretionary funding until 1998. Congress authorized a roadmap study so that the nation could study where we should go with this project and how long it would take and how much it would cost and what we could do for the nation with it. It evolved in 1999, in 2000, and 2001, and current into the Advanced Accelerator Applications Program. The Advanced Accelerator Application Program, through the program, we are joining the rest of the world in a research effort that they have been conducting as well. The map here, see if I can, shows many of the nations that are involved in transmutation research. So we're joining the rest of the world in that effort. Now, if we look at what we have and our options with used nuclear fuel, it drives us to this realization that we need to consider options. When we did the roadmap, we knew that by the 2030s we projected by the 2030s we would have something like 87,000 metric tons of used nuclear fuel in the United States. And the reason we knew that we used that quantity was because at that time that we did the roadmap, we projected that all of the nuclear power plants in the United States would shut down at the end of their 40-year lives. However, with life extensions, we now project about 140,000 tons by the end of the lives of those same reactors. And that means, and if we look at the Nuclear Energy Institute's vision that they've recently published, the projections are something like 120,000 tons in the 2030s and 180,000 tons in the 2050s. A terrific mass, a tremendous mass of used nuclear fuel, and we know that, for instance, the Yucca Mountain repository is being designed for about 70,000 tons of commercial used nuclear fuel. So this greatly exceeds that. What do we do with it? Well, we have several options. One of those is what we call the once-through-fuel cycle. It's, of course, an open cycle because it doesn't ever complete the circle. Or we may choose various options to reduce the quantities of waste, to reduce the radiotoxicity of that waste, to reuse the materials in that used nuclear fuel, and to recycle things like uranium and plutonium. We might do that in MOX-fueled light water reactors or high-temperature gas-cooled reactors. We might do that using accelerator-driven transmutation, which is the concept that Los Alamos had been pushing as the single way. Or we might do that in fast reactors, which include breeders, but if you're just trying to destroy fissile material, you wouldn't use a breeder reactor. This is today's option. Some people call it burn it and bury it. I don't like to use the term burn because I deal with the public, and the public thinks I'm talking about putting waste in a garbage can and setting it on fire. We don't like the public to have that kind of an impression. Direct disposal faces many challenges. It has political opposition. As a matter of fact, the political opposition living in Las Vegas, Nevada is quite apparent to me. It has some public acceptance problems. There are licensing and regulatory concerns. We haven't answered all of the issues. We think we can answer all of the issues, but we still have a long way to go to do that, to bury used nuclear fuel in a tunnel in the mountain in Yucca Mountain, Nevada. And there is still considerable uncertainty in projecting out for hundreds of thousands of years, both in the releases from this kind of repository, as well as things like what is the proliferation risk from putting 100,000 tons of used nuclear fuel that contains 1,000 tons of plutonium into a mountain and leaving it forever. The transmutation of that waste offers potential solutions to these challenges. What is transmutation? It simply means a nuclear transformation. It changes the contents of the nucleus, either the number of protons or the number of neutrons, or both. Natural radioactive decay of the nucleus is a form of transmutation. So it can occur naturally when one nucleus decays into another nucleus, or it can be driven by proton or neutron reactions in the nucleus. We've been doing this since before World War II. Physically, it isn't difficult. Turn lead into gold? Yes, we can turn lead into gold. We just need a source of neutrons and a lot more money than the gold is worth. Most of the long-term hazards from used nuclear fuel are due to just 1.1% of that mass. Okay? We have about 96% of used nuclear fuel is uranium. That uranium, if you could separate it out completely clean, is barely more reactive today than natural uranium. And if it decays for a few years, it actually would become about the same as handling natural uranium, so that you could reuse that. So if we can separate that out cleanly, we can set it aside for future use when we need it. 3% is stable or short-lived fission products. We can separate those out, let them decay, and dispose of them as non-radioactive materials. 0.3% is cesium and strontium. These are some of the more troublesome of the isotopes of used nuclear fuel. 0.9% plutonium, 0.1% other actinides, minor actinides like neptunium and americium, and 0.1% is iodine and technetium, which is our other problem isotopes. To handle this material, if we could take these problem isotopes, the plutonium, the minor actinides, and the iodine and technetium, and put them into a specific reactor that's designed to destroy them while yielding energy at the same time, we follow a process like this, where we have a neutron from the reactor, strikes the plutonium or minor actinide, which absorbs that neutron and fissions into two fission products. So we have now new... Go back. We have now new fission products to deal with. We also have another neutron, and if we have a near-critical reactor or a critical reactor, we can maintain a chain reaction. We also could take some of the extra neutrons and absorb have technetium absorb those. Technetium decays to ruthenium with a very short half-life, and ruthenium is stable. So you take something that's a problematic toxic hazard for a waste repository, and you turn it into something that is non-radioactive. Same thing with iodine. It absorbs a neutron, decays in seconds, I believe, is the half-life for iodine, for the iodine decay, to a stable form of xenon gas. Inert gas, not a chemical problem, not a radiation problem after you absorb it. And we keep going through that process. So what we need to do is to figure out how to build a system that can do this. The challenge then, that we know the physics, we know the issues of this, we know what we have to deal with and what we have to work with. The challenge is to do it effectively, and that means thorough, clean, safe, and cost-effective. To do that, we need nearly 100% conversion of those materials. We need very low losses in processing streams because you're going to end up processing this stuff, repeatedly recycling, and if you have a large loss each time, and large being fractions of a percent, then you're going to have a lot of material that's going to be in a waste stream that you're still going to have to dispose of. We have to be able to do this accident-free, which means we have to create systems that are as safe as today's nuclear power plants or safer. We need to reduce waste toxicity and volume. There's no sense in doing this if you're going to end up with more stuff to bury than what you got rid of. So one of the challenges is to reduce to some level the waste toxicity, the volume of waste, maybe the heat that's being generated by the waste so that you can manage the waste better, and which is one of the advantages of this technology. And we need to have a minimal impact to the cost of the nuclear fuel cycle. Now, to some people, that means zero. Okay, well, we don't recycle other things for zero cost. We spend billions of dollars recycling inert materials like plastic jugs and newspapers and things like that aren't harmful. So to me, I don't think we have to have a zero cost for recycling used nuclear fuel. It benefits nuclear power and it benefits the nation, and that ought to be worth something. The AAA mission then is to conduct research, development, and demonstration of the transmutation of used nuclear fuel. We haven't figured out how to do that yet. That's part of our research program. We also are looking at building a test bed to conduct nuclear R&D. We want to create the capability of producing other isotopes, for instance, isotopes that could be used by the medical community to do medical research or to do medical therapeutic techniques using new radioisotopes that you can create with these high-energy particles. And we want to use this program, take advantage of the attractiveness of transmutation to students and recycling to students, and to use this to increase our nuclear infrastructure and the future of nuclear power in the United States, to increase the probability that new nuclear power plants can be built in the United States. So we have multiple missions here. The transmutation strategy then is to take used nuclear fuel and break it up. You have to just like in the Purex process for recycling and processes that are used in Great Britain and France, we need to partition the used nuclear fuel into its components. Separate out uranium, separate out plutonium, or leave the plutonium and the other minor actinides mixed so that you reduce proliferation risk, and separate out the other materials and figure out the best way to transmute those materials or use them. We can discard the uranium if we do this cleanly, and we figured out that we can do this cleanly. We can do about 99.999% pure uranium now, and discard the stable elements. They don't need to be buried in a high-level waste repository. We may decide to bury the uranium for now, and if we want to dig it up in 50 or 75 years and use it, we can do that. Or we may set it aside, put it in some kind of a stable chemical form like an oxide, and just set it aside. We need to then form transmutation fuel from the long-lived radionuclides. We've got to figure out what that fuel needs to be. We're going to take the plutonium, the neptunium, the americium, curium, hopefully leave those all mixed together and put them back in a reactor. Or we may decide that we know how to do this well enough that we can separate the plutonium, make fixed oxide fuel, and feed it to a light water reactor, or feed it to a gas-cooled reactor, or feed it to a fast reactor. So there are lots of options, and then the R&D program for the next 5 or 6 years is going to be examining those options. Once we've made those into fuel, we have to put them into some kind of a system that will transmute them. That may be a fast reactor, it may be a gas-cooled reactor, maybe a light water reactor, it may be a accelerator-driven transmutation system. And then what we have to do after that is we still have nuclear waste to manage. Okay, we have to manage those remaining short-lived waste for just a few hundred years instead of the tens of thousands of years that we're talking about today with the Yucca Mountain project. So the ATW technology, the accelerator transmutation of waste, and other transmutation technologies can lead to reductions of nuclear waste. by, here we go again, okay? Our byproducts of this are going to be some isotopes and electricity that is worth billions of dollars. As a matter of fact, one of our ATW scenarios that we figured out we would produce about a third of the electricity that's been produced in making the waste you could produce by transmuting just the minor actinides and the plutonium, just the transuranics. We'll have less waste to store, with significantly reduced quantities of plutonium, not zero, but much less than it will be in used nuclear fuel and other transuranics, and a major reduction of long-lived fission products. Out of 70,000 tons of uranium, you would have about 67,000 tons. 70,000 tons is what's intended for the Yucca Mountain Repository by law. You would have about 67,000 tons of uranium that could be recycled, and we think we can reduce the volume and the toxicity of the radioactive waste substantially. We just haven't figured out what substantially means yet. This is a graph of a very, very careful system study that has been done of the projected impact of burying used nuclear fuel at Yucca Mountain. This is the plot without treatment, okay, and we see the dose rate at 20 kilometers away from Yucca Mountain, including all exposure pathways, for the first million years after the closure of the repository, and we get dose rates up into the hundreds of millirems per year at about 200,000 or so years. We see that we stay below that for the earlier time. Just by treating the unused nuclear fuel, we get to this level here, an order of magnitude. That means this still includes burying the defense waste, and that's why this isn't 4 orders of magnitude. If we didn't bury the defense waste, the impact here is for this line to drop by 4 orders of magnitude. To accomplish this mission, we're going to need 3 kinds of technologies. The first is the partitioning or separation of the fuel and the creation of waste forms from that separated fuel. One of the advantages you get when you go through the process of separating fuel into its components is then you have a choice of what you're going to bury. You're not choosing to bury used nuclear fuel the way it came out of the reactor after 20 or 25 years. You're taking these materials and you can say, I can now choose the optimum waste form for each of the streams that I've separated. If I've separated a stream of metals, I might be able to mix those with the tremendous quantities of zirconium that come out of reactors and create some kind of a zirconium metal complex that I can bury as a metal, very long-life material. I might make glasses, ceramics, or other waste forms as well. And we also, for the chemistry, we've got 2 options. We've got a couple of options we're looking at. We're looking at aqueous processes like Purex, what is now called Urex. Urex is like Purex, except you don't separate the plutonium from the other actinides. And we have molten salt processes like they use in the integral fast reactor program. The second technology we need is accelerators. We've looked at cyclotrons. The Europeans are looking at having an accelerator-driven system that's driven by a cyclotron. We believe a linear accelerator has advantages in terms of the power and energy of the particles and its ability to withstand the radiation that you create in this process. So we think the linear accelerator is the way to go. But to build a linear accelerator, you need a whole lot of materials and space, whereas a circular accelerator occupies much less space. So there are trade-offs. We also need to look at the transmuters themselves, either critical reactors as a recycling through a critical reactor, maybe 1 time, maybe 5 times. Those are options that have to be investigated. And we're also looking at subcritical transmuters that are driven by some kind of an external neutron source. That typically would be an accelerator with a very high energy protons that I'll discuss a little further. But I've got 6 different kinds of subcritical transmuters, and I've mentioned 4 or 5 other kinds of reactors. So this is a terrific engineering systems problem that we have to do, as well as developing materials, developing separations processes, developing cooling systems, doing reactor analysis, developing new kinds of fuel that we have no experience with and no experimental facilities to test them in. First of all, separations and waste forms. We're looking at a couple of processes that I mentioned. One is aqueous. The UREX process is being investigated by Argonne National Laboratory for the AAA project. It may be preferred for the separation of used LWR fuel. The reason we're looking at it instead of the molten salt process is because the molten salt process is a batch process. And if you're looking at, processing 80,000 tons of material in a batch process, you're talking about a lot of batch processors or a lot of batch processes, one of the two. And it's better if you can use a continuous process, which is the aqueous process is. The UREX process, as I said, does not separate plutonium from the minor actinides. Okay, that reduces the proliferation risk of having pure plutonium in any form, anywhere in the world. Pyroprocessing, similar to the integral fast reactor, is using molten salt. You create a very high temperature, highly corrosive molten salt mixture, and you dissolve the uranium, plutonium, other fuels in it, and then you use electric potential to separate materials. And you can separate things very cleanly by doing this. We can take out all the minor actinides together on one side and leave the uranium in the mix, or we can take out specific radionuclides by adjusting the voltage properly. And that probably will be used for used fuel from the Accelerator Transmutation of Waste process, where you have much smaller volumes of material because you've reduced you've reduced the mass of material that you're handling from 100 tons of uranium, for instance, down to 1 ton of minor actinides. Okay, so the quantity of material there is much lower. There are other processes being looked at. FLEX stands for fluorine extraction. It appears there may be some very clean ways to use that. As I mentioned, one of the advantages of this is that you separate the problem isotopes, transmute some of them, and then you have others that you can combine to create long-lived, non-hazardous waste forms. We can, as I said, combine some of those with massive amounts of zirconium, put some in vitrified waste, and we'll be able to optimize that in the future. Accelerators, I don't have a picture of an accelerator, but an accelerator is basically a long line of cavities that you drive with microwaves, and the microwaves cause, as protons go through each of those cavities, they get accelerated a little bit in energy, and you go from 0 electron volts up to millions of electron volts, or even billions of electron volts. So we can create very high energy protons, and when you smash a high energy proton into a solid heavy metal, you produce a lot of neutrons. And the number of neutrons you produce depends on how heavy the metal is and what kind of metal it is. If it's a metal like uranium or plutonium, of course, you're going to produce more neutrons than you will smashing it into something like lead or tungsten. We're looking at energies between 600 and 1,000 million electron volts, okay, between 0.6 and 1 giga-electron volts, and milliamps of current. And if you multiply those two things together, you're into the megawatts of power range. The product then is a megawatts of beam power, and you're talking about putting a megawatt of power into something that's fairly small. So if you think about producing a megawatt of power in something that's made out of metal, steel for instance, now you're going to have to start thinking about, how do I cool something like that? Now, how do I keep that thing from getting so hot that it just melts? And how do I keep these particles from destroying it? Remember, we're embedding hydrogen. Hydrogen is a problem in all nuclear processes, hydrogen embrittlement of materials. And we're purposely embedding, huge currents of hydrogen into steels and tungsten and things like that. So we have to think about the engineering challenge that's going to be if we actually build a system like this that we expect to run for 60 years, for instance. This thing is going to be big, and it's going to be very expensive. And now we have to turn this proton beam current that comes out of the end of this big, long accelerator into neutrons so that we can drive these transmutation reactions. We wouldn't want to try to drive the transmutation reactions with the particles directly, because you're going to have to get through something to get to the fuel, because you've got to keep the fuel from getting back to the accelerator. So we've got to have some intermediate process, and that is what we call spallation and evaporation. The protons will strike a heavy nucleus. They either knock out at very high energy, they knock out particles. These are 600 million electron volt neutrons, and they strike a nucleus and they just blow it apart. As they slow down, these knocked out particles then start creating cascades of neutrons and other particles. There's pions and kaons, and you have to calculate all those in this kind of a calculation. It's not a simple neutron transport calculation anymore. As soon as that proton hits the nucleus, you've got 30-some different types of nucleons that you have to calculate in a transport code. They create a cascade then of neutrons of ever lower and lower energies, and eventually you get to where the nucleus will be excited but not blowing itself apart. And then that nucleus, those nuclei then just sort of boil off neutrons at, the 5 to 10 MeV range. So you end up with a spectrum of neutrons that's between fission energy and 600 or 1,000 million electron volts. And we've got to be able to do computational work that will do that. We're still working on the codes to make that possible, and we still have to validate those codes. This is a picture of the energy yield versus the neutron yield versus the proton energy. And we see the scale over here is 0 to 200 neutrons per proton. And what we're looking at for an accelerator transmutation of waste beam energy is something like this, but for an experimental facility, we're back here in the 600 million electron volt range. Okay? And I've got 4 different kinds of material over here. If we used uranium, as I said, you've got a much higher yield, but it's going to be, you're going to have a very radioactive uranium material left over afterwards, which probably we wouldn't want to do that for an experimental facility. It may be the way to go for an actual transmutation reactor. But we're talking about working in the range here of 30 to 40 neutrons per proton in a production facility, and 10 or so neutrons per proton in an experimental facility. So we've got the separations, we've got an accelerator that gives us the materials and the source to drive some kind of an experiment. This is an early model of a transmutation reactor where you would have an accelerator beam coming in. This would be an earth berm of some kind. You'd have a beam expansion and turning module. You would drive the beam down, and this would actually be your subcritical blanket. Heat exchangers, pumps. This might be a liquid metal cooled system with the pumps inside of it. That's sort of what we're hoping for, is either sodium cooled or a lead bismuth cooled. We're doing a lot of research at Los Alamos on the lead bismuth coolant. The major challenge, though, for the transmuter, as far as we're concerned, is developing the fuel. We've looked at a lot of different types of fuel, oxides, metallic fuels where we mix plutonium and the other transuranics with zirconium. One of the problems with the metallic fuels is at high temperatures, melting points of metals, americium is very volatile. So if you've got a process that you're trying to cast a molten fuel, the americium evaporates, and you get americium all over everything. So we've got to figure out how to keep that americium from evaporating in that type of process. Pyrolytic carbon-coated oxide. Oak Ridge National Laboratory has a significant part of the accelerator applications, Advanced Accelerator Applications program, to look at the coated particles, making coated particles and having a coated particle transmuter or a coated particle reactor. We've looked at molten salt reactors. We've looked at nitride fuels and carbide fuels. Many of these fuels are, they're non-fertile fuels because you don't put uranium in them, and we've developed non-fertile fuels in the past, but not for this kind of application. Structural materials, as I mentioned, we're going to be irradiating these in huge fluxes of neutrons and protons, and very peaked, because the source will be in the center. You're not going to have it spread out over the entire reactor or transmuter. So we have to look at new structural materials. We've got to look at structural materials in sodium, structural materials in lead bismuth. Lead bismuth is very corrosive, and thus you control very carefully the oxidation state of that lead bismuth. The Russians use this in their nuclear-powered submarines. But what they have to do is they have to come back in. They can't stay out at sea for a long time. They have to come back in and take that lead bismuth and completely clean it and put it back in the submarine, and then they can go back out to sea for another short while. Or the lead bismuth will eat the steel. And it will eat through, lead bismuth that's not conditioned will eat through a steel pipe in about 3,000 hours. Just eat it up. And then we've got, our coolants. We've got sodium, we're looking at water, helium, and the lead bismuth eutectic. So we're looking at all these different kinds of reactors. We have not made a decision. Sometime in the next few years, we'll make some down selections. And we'll say, okay, we think this system is the best way to go, and that system is the best way to go. The subcritical capability, we think, adds flexibility. Nuclear systems have always operated critical, nuclear production systems. We think this adds flexibility because you can drive systems with very low fissile content or a high non-fissile burden. You can operate with fuel that can make critical systems unstable because you can turn the reactor off and your source of neutrons disappears. And you can compensate for large uncertainties or reactivity swings by turning the power of the accelerator up or down. This subcritical operation addresses some of the fuel cycle issues. We can jumpstart systems that don't have sufficient fissile fuel content. In other words, if we wanted to start up a thorium fuel cycle without using nuclear reactors, we could put thorium into a system like this and start hitting with neutrons that are created by an accelerator and breed material into that thorium until we had a self-sustaining system. We can support advanced fuel cycles by transmuting their wastes. And this is probably where we're headed with this project. And close down cycles with depleted fissile content, and that's also part of where we're headed with this project. We've done some very careful systems and scenario studies. This is from the roadmap, and it shows basically what we're talking about here. This is about a seventh of that, or an eighth of that quantity of fuel that I mentioned that would have been created by today's reactors had we not extended their lifetimes. So if you had 8 plants like this, you could handle all of the used nuclear fuel from the United States system. And this shows, the streams of how much material you would be separating out in tons of short-lived waste, tons of uranium to recycle, fresh fuel that would have to be processed, and it wouldn't all be transmitted the first pass-through, so you're talking about recycling sometimes several times. You would also generate a tremendous amount of electricity. One of these systems would produce about 2,000 megawatts, supporting about 10 or 15 nuclear reactors. It would also run for 60 years, and by the time we get all this done, we're talking about something like 2110 or 2120. By the time we do all of the R&D, develop the systems, build them, and transmute all of this used nuclear fuel. Some people think that's too long. Other nations are looking at this, as I said. This would be, this is our concept, to use only an ATW. This was our first concept. And basically, you end up with just waste. In France, they're looking at a multi-component concept where they recycle plutonium in a fast reactor. The minor actinides go to an accelerator-driven system, and you end up with waste. And plutonium is also recycled, as everybody knows, the first time. And most people, there are a lot of people who don't realize that France only recycles their fuel once. Because they make mixed oxide. That mixed oxide is not processed. Okay, so that's where this comes from. Now you would take that fuel, reprocess it, and feed it to a fast reactor, and that is their intention actually. And then the minor actinides would go to an accelerator-driven system. If you only send the minor actinides, you're talking about 0.1% instead of 1%. So, I said we would need 8 of those facilities. You would only need 1 of those facilities to handle all of our used nuclear fuel in the United States if we had recycling in fast reactors or recycling in light water reactors. There's also the minimal scheme in Italy where they have they add thorium to the plutonium and minor actinides, and then they have a self-sustaining energy amplifier system that creates as much fissile material as it destroys. It's not really a breeder because it's not making more fissile material, but it is a self-sustaining cycle here. They would also recycle some of the plutonium. In Japan, they have what they call the double stratofuel cycle. The minor actinides and the long-lived fission products would go to an accelerator transmutation of waste and the light water reactor would recycle plutonium and also recycle uranium. Okay, so that you have two different kinds of light water reactors operating. So there are lots of these concepts floating around, and a lot of people working in the world, and we're participating with those other international groups now under agreements that have been signed between the United States government and other governments. This is a graph. I showed the roadmap or the schematic of the ATW roadmap system. This is a map of what you would have if you had a multi-tier system. In the first tier, the 0th tier is today's light water reactors. The first tier is some kind of a reactor. We don't know whether it's a thermal spectrum reactor or a fast reactor. This one is a thermal spectrum reactor. Then you would have a separations process here. You would have fuels and targets fabrication for an accelerator transmutation of waste product, and you would have all of these waste streams going into a repository. So although you've produced less radioactive materials, you've kind of complicated the picture because you've got multiple streams of materials that you're going to be putting into a repository. So you're going to have to figure out how all those things work together. It may, in fact, be simpler to manage this facility than it is with the today's heat-producing radioactive waste. Oh, too far there. So partitioning and transmutation are going to be evaluated versus 4 goals. Those goals are to reduce the toxicity of the used nuclear fuel within the lifetime of man-made containers. Okay, we know how to build structures that will last a few thousand years. We've got them standing around all over the world. The churches, the pyramids, the Parthenon, other structures like that. We know we can build structures that will last a few thousand years. We don't know that we can build structures that will last tens of thousands of years. We want to reduce the long-term dose to inhabitants by transmuting the mobile elements, deplete the actinides to reduce their attractiveness for proliferation, and improve the prospects for a nuclear future. Okay. The first of those goals, if we look at the relative ingested toxicity of, this is the versus time, there's 1,000 years and 10,000 years of nuclear reactor waste. Compare that to natural uranium. This is the metric that the Russians use. And this is the toxicity, the relative ingested toxicity of natural uranium ore. And we can see that if we just take the actinides out, that we can reduce the toxicity of that material in about 300 or 400 years to be the same as natural uranium ore. Now, we can't remove 100% of those actinides. We're thinking we can remove 99.9%, but that's got to be determined by future studies. To reduce the maximum long-term dose, we can do that by transmutation and also by the waste form optimization that I mentioned earlier. And again, we can compare that versus the natural background good dose. So we have a metric that we can measure our systems that we're trying to develop against. We need to deplete the content and mix of actinides in the waste stream rather than, it's very difficult to assess numerically what is the risk of burying used nuclear fuels as far as proliferation is concerned. We have a project with the University of Texas, Arlington, University of Texas at Austin, where they're developing methodologies to assess the proliferation resistance of different fuel cycles over long periods of time, not just today. We know if we keep the stuff in used nuclear fuel today, it's very radioactive, it's very proliferation resistant. If we separate out the plutonium, that's going to be more proliferation resistant today. But what about if we integrate the proliferation resistance of a repository containing plutonium over 10,000 or 100,000 years versus the reprocessing, removal of that plutonium today or in the next 10 or 20 years? What is the integrated proliferation resistance there? We also want to improve the prospects for nuclear energy, and if we integrate that over time and across borders, we see that we think we can develop simpler, cheaper repositories, have minimum near-term proliferation risk and no long-term proliferation risk, and we can do it with a marginal cost impact. We've got a lot of engineering studies to do to determine that, and we believe the near-term environmental safety and health burdens from this process are manageable. They're not zero, but they are manageable. Why invest in this? One is public support. Everywhere I go, the general public thinks recycling is a good idea. It doesn't matter what you're talking about. You can talk about recycling nuclear fuel, you can talk about recycling plastic jugs, aluminum cans, cat food cans, whatever. The public supports the recycling of materials. They believe it's environmental and it's good resource stewardship. This is especially true in Las Vegas, Nevada. The general public in Las Vegas, Nevada knows about transmutation. It's just completely baffling to me. Many people think it means you won't be putting anything in Yucca Mountain, which is not true. We try to, every time we give presentations on this to Las Vegas community, we tell them that, transmutation does not mean we don't need a repository. It may mean that we don't need Yucca Mountain. It may not mean that. And it certainly, isn't going to save us any money going off and studying another repository in addition to or instead of the Yucca Mountain repository. It augments our current waste management strategy. Instead of talking about having to manage this high heat-producing nuclear fuel that will be put into Yucca Mountain and digging more drifts, we may be able to move things into Yucca Mountain and back out, process them, and more easily manage the facility. It brings the U.S. back to the forefront in nuclear science and technology. Okay. It puts us out in front as leaders in the world in nuclear science and technology. We were losing that role because we weren't participating in we weren't being the leaders in the development of new nuclear reactors. We weren't being the leaders in the development of nuclear science and technology. But this puts us back, and the rest of the world is waiting for us. They're anxious for us to participate in this R&D with them. They're ready to spend money in the United States. I hit the button again, didn't I? And one of the major benefits, and possibly a more important benefit of this than transmutation, will be the spin-off technologies. The medical isotopes that can be created, they may be as significant as the transmutation of waste. Other nuclear technologies, one of the things we talk about is building a neutrino lab, will be the highest neutrino production facility, highest rate of production of neutrinos constant over time, steady state over time if we build one of these accelerator-driven test facilities somewhere in the nation. That somewhere could be Los Alamos National Laboratory, where the Los Alamos Neutron Science Center is now with the Lance Accelerator, 800 million electron volt accelerator. It could be at Savannah Riverside, it could be at the Nevada Test Site, it could be at a number of other sites in the United States. It's a big project. It's going to be at least $1 billion project to build a facility like that. So, whether we end up doing that in the next few years will be determined by what the intentions of Congress are. But the first part of this, will be to do the R&D to get to that point. So the project is going to have about 5 or 6 years of research and development before we make a decision on where we want to go beyond that. Why not invest in transmutation of nuclear waste? Well, first of all, it's expensive. We know it's going to be expensive. We're probably talking about billions of dollars to do the research and tens of billions of dollars to develop the first prototype facility and hundreds of billions of dollars of cost to actually do the job over the lifetime of the fuel that we'll have. But we may at the same time be able to generate hundreds of billions of dollars worth of electricity. That's a careful balance there, whether we think it's worth a little bit of extra expense or if we can figure out a way to do it and make money. That's one of the things we're working on in our research. There are other transmutation concepts. They may be more difficult to implement. They're less flexible in transmutation by using accelerators and narrower in scope. but they may do the job. And that's probably what we're talking about the Tier 1 now is let's get rid of most of that fissile material in a system that we know how to operate today, a gas-cooled reactor, a light water reactor, or some other system, or a fast reactor like the integral fast reactor. There's uncertainty in this. Always in a new scientific endeavor you've got uncertainty, but the success of new technologies always entails that. And there is a proliferation that we need to work on. We need to determine, if we can do this with an acceptable level of proliferation risk for us in the United States. We do this by looking at technology readiness levels. We look at the R&D that we need to do by looking at technology readiness levels, which is a system that was developed by NASA. Okay, and you have technology readiness levels for one, where you have analysis that's based on basic principles, reactor physics calculations, for instance, materials, what we know about materials today. And you go all the way up to, I think it's a 9 or a 10, it's a 9 over here, okay? And a 9 means the technology readiness level is sort of like a satellite that's orbiting in space. You've tested it, you know it works, you know what the problems you had with it. And the intermediate levels are where you've done component and phenomenological testing in a relative environment, or in a relevant environment. When you get to about level 7, you're ready to build a prototype system and field it. So these are the levels we're at today in many of these technologies. Okay, we look at lead-bismuth cooled targets. We're at this end of the spectrum. Water-cooled targets, we know how to make those already. Okay, we've built prototypes and tested them. There are systems in the world operating on it, being driven by proton accelerators in the United States and Europe. Fuel fabrication performance. The non-fertile plutonium and minor actinide-containing fuels were at this point. We know how to make mixed oxide fuels, and we know how to make integral fast reactor ternary fuels. Okay? Separations. Okay, get away from there. What do I got to do? Okay, we're going to go to previous, and then we're going to go to next. How's that? Okay. Pyroprocessing. We know how to do, for instance, the Urex process is very far along. We know how to do Purex. Urex is simply changing the chemistry a little bit so the plutonium doesn't get separated. Pyroprocessing, we've done experiments, but the minor actinide processing has got to be developed further. Blanket coupling. This is a big area here. We have very little experience coupling accelerator-driven neutron sources with a subcritical, with a target and a blanket, and calculating and measuring the results of what those will be. So we've got an experiment we're planning right now where the Idaho Accelerator Center is going to field one of their electron accelerators to make photoneutrons, and those photoneutrons will be used to drive the treat reactor at Argonne National Laboratory West. So we're actually going to start doing experiments to determine the coupling between the accelerator and the reactor and see if we can calculate the results of that. Blanket technology. The Russians know how to use lead-bismuth eutectic. We know a lot about gas-cooled fast spectra. We also have quite a bit of sodium-cooled reactor experience. So we're up at a higher technology readiness level with those kinds of things. We've got a lead-bismuth eutectic experimental loop running at, was just commissioned last December, is running at Los Alamos National Laboratory. We paid the Russians about $1 million to build an accelerator target that we had intended to bring back and field at Lance, a lead-bismuth cooled accelerator target. We've decided not to field it at Lance. Instead, we're going to bring it to the University of Nevada at Las Vegas and use it as a thermal hydraulic test loop there. And the accelerator technology, this was done, we spent almost $600 million developing the accelerator for the acceleration of production of tritium project. So we've spent a lot of this money. We developed a low energy demonstration accelerator that was tested and worked beautifully at Los Alamos. So we've done a lot of this work as well. The one thing the one problem we have with accelerators is they're not reliable, and we need to do a lot of research and development to make them reliable. I probably need to get things wrapped up here in the next few minutes. This mission is going to require the optimum use of the nuclear infrastructure that we have today because we've lost a lot of our nuclear infrastructure. We need a new test facility. We have to use existing facilities, and that means both our facilities and international facilities in France and Russia and Japan and other locations. And we have to use all the people we can access. National laboratories, there are 8 national laboratories involved in the AAA project today. Internationally, we have a cooperative agreement with France. We're working on agreements with Russia and other nations. Universities, we have 5 universities under contract. We will have a 6th university under contract very shortly, and we have fellows now at probably, we have 9, and we have fellows, 10 more fellows who are in the process of being selected for the AAA project. So we have to use all of those people. The facilities to provide the proof of principle and proof of performance will be, out over the next many years. We can do scaled experiments at Lance, Treat, as I mentioned, Mazurka, MTL, the Advanced Test Reactor, Phoenix Reactor, the Bohr 60 reactor in Russia, and the Blue Room and hot cells are at Lance. In the longer term, we're talking about building an accelerator-driven test facility or a university research accelerator, or the acronym changes every couple of weeks, so I'm not sure today what it's actually called. But a facility for future research on this topic. We have 7 major work packages with the CEA in France, where these are the types of research that we're cooperating with the French doing. Let me go past a couple of these things. We have, in university programs, we have $7 million in university research in this project this year. We have directed university research at Michigan, Berkeley, Texas, Austin, and North Carolina State. We have a fellowship program, as I mentioned. 10 fellowships are awarded each year. We have the University of Nevada at Las Vegas and the Idaho State University, a total of $6 million at those 2 universities. And we're getting ready to start a new university research program that will be competitive, peer-reviewed proposal process to directly support the R&D that's being done at the laboratories for this project. $7 million this year. We think we'll go over $10 million next year, and last year we had more than 80 students in the project. I don't know how many of you went to the student conference at the Reno A&S conference, but for the first time there was a student conference in conjunction with the American Nuclear Society conference last November in Reno. More than half of the papers that were presented by AAA-supported students from all over the country. In conclusion, the AAA program will provide us a sound foundation to assess the options for transmutation, whether we're going to go with a 2-tier or a 3-tier or a more tier system than that, and how big the accelerator would have to be from that. Well, it gives us an ability to support national security issues, to develop isotope production technology that can benefit the medical community as well as other non-power nuclear communities. And it greatly strengthens our nuclear infrastructure. This is preparing students and faculty members and laboratory people to work in these different areas for the long period, and we're able to attract using this AAA project. My experience has been that it's very attractive to students. With that, I would like to answer any questions you may have.
Okay. Presentation's over.
Yes.
How come you're not soliciting DOD?
Because the DOD doesn't want us to. We certainly will look at it in the future, I'm sure, but right now it's a big enough challenge just to look at using processing used nuclear fuel. Physically, technically, there's no reason that you couldn't.
But I thought it would make sense from the point of the cost.
It would make sense from the point of the toxicity of the repository.
The tons of waste that you projected included DOD waste or not?
No, that was commercial used nuclear fuel. Other questions?
Any other questions or comments? You forgot to mention what you're going to be doing this afternoon. There are some students.
Oh, that's true. For the students who are here and have an opening at 5, I will be making a presentation on Los Alamos's, a recruiting presentation for Los Alamos National Laboratory over at the Dunford Hall at 5 o'clock. We currently have 366 positions open for external hire. That means people who don't currently work at the laboratory. It's wide open at Los Alamos. Plus we have, we hire students in the summer. So I'll be making a presentation over there at 5. No, as a matter of fact, it isn't. A large fraction of the work that's being done at Los Alamos is not classified, and we have a lot of non-nationals working at Los Alamos. And that's especially true in Lance, the Los Alamos Neutron Science Center. You don't need a secure badge to get in that area. You do have to have a badge, but you don't have to have a secret clearance or anything. And we do have non-nationals working on this project.
Any other questions or comments? We did get a question from our cyber audience. It came early in your presentation, and then you. During the latter part of your presentation, you actually answered his question.
Okay.
And so he sent me another message and said, please ignore my first question. So we are getting good feedback from our cyber audience. As most of you know, we do have refreshments downstairs, and everyone is invited, but before we adjourn for refreshments, let's give Dennis a round of applause. Thank you.
Thank you.
I'll get that paper for you.
Thanks.
Yes.
Do you want to go further?
I earlier he was sitting down on the